The whole topic as soon as the August term starts. So, because we work out a new schedule and then. So, the first request is all of you here who want to continue in the August term, first send me a blank mail so that I will have a mailing list, because the old mailing list is totally different from what it is now. So, first send me a blank mail, title and subject as analysis, okay. Then I will, once the first 2-3 days of August settles down and all the timetables are known, then we will have one meeting in the evening to fix the timings for this course. At that time I will start regular function theory, continuous functions, derivative, limits, continuity, differentiation, etc., etc. So what I want to do today is, having talked about topological properties and the real line, I will introduce one more very interesting notion a topological notion on the real line, which has its generalizations, and it leads to some very, very fascinating results in analysis. Okay. The notion is called the idea of nowhere dense sets. Okay. I would first start, so our aim today is to look at what are known as nowhere dense sets. And look at what it means, and then see its role in analysis. Finally, I'll give you one very interesting example, which is in the simplest form. I'll give, very easy to see within course. Okay. So the idea is the following. Let's look at, again, start with the real numbers. Whenever I write that, the usual metric, okay, real numbers with the usual metric, the distance between 2 points is mod x minus 1. So that is always understood unless otherwise stated. Now I am going to look at 3 examples. Any questions? Look at the following 3 subsets. One I will call S1, which is Q, 2 S2, which is Q intersection, say 0, 1, the interval 0, 1, and 3 the natural numbers. Look at these 3 subsets of the real line. You already see visually something is happening. One is, look at S1. Wherever you go on the real line, you can't avoid them. That's roughly what we know. What do you mean by wherever I go? A typical patch in the real line. A typical patch in the real line is an open interval. Topological patch is a real line. The simplest topological patch we can take is the interval. If we take an open interval, there will always be a fellow in this. So roughly I will state, first of all I state it this way. Wherever we go in R, we cannot avoid well, what do I really mean by that? I formally write it like this, that is, for any open interval, let me write it always in this form, A plus epsilon, A minus epsilon, A plus epsilon. Any open interval has a center and a length. So take any open interval A minus epsilon, A plus epsilon. Well, it may be that A itself is not rational. So we may have to avoid it. So therefore some piece, there will always be some piece. Here is A, here is A minus A, here is A plus epsilon. Now this whole interval, this fellow, I can take any piece for that matter, in fact that piece itself. There will always be a small piece which contains the rational numbers. In this case, the piece can be taken as the whole thing. There is a sub-open interval. In fact, here he can take it as the original interval itself. So there is an open subinterval such that, let me call it as in our the center A and radius, this is the usual notation. I use the word. And here I will call it a subinterval, say I prime epsilon. Okay. Prime is bad, it means I hat epsilon, such that I hat epsilon intersection Q is non-empty. In this case, I hat epsilon can be taken as I epsilon A itself, its intersection Q is non-empty. So wherever you go, you cannot avoid them. What do we call such sets? They are the dense sets. Wherever you go, you cannot avoid them. So this is what is known as everywhere dense. We use the whatever small portion you randomly pick, for anywhere on the real line, there will be a fellow sitting there, snooping. So that is what is called everywhere dense. Now the difference between that and this fellow now is the fact, well, it is not everywhere dense. You could certainly go to some place and avoid S2. For example, if you go to the interval 2, 3, there is no point of S2 there. So you can certainly go to some places where you can totally avoid this fellow S2. But however, there are some places where you cannot avoid it. Like for example, you go to somewhere inside 0, 1, then you are not able to avoid S2. So this is what is called somewhere dense. It is somewhere dense, some portion in which it is dense. So this we will call as dense in R, that will be dense in that part, namely 0, 1. 2, S2 is not everywhere dense. It is, let me put it this way, it is somewhere not dense and somewhere dense and somewhere else dense. It is in some portions dense and in some portions not dense. You can avoid these points if you go to some places, but if you go to some other places, you cannot avoid that. So, somewhere not dense is the negation of everywhere dense. What is the negation of everywhere dense? That means wherever you go, you cannot avoid them. The negation of this is somewhere I can go where I can avoid them. Not that wherever I go, I can avoid them. That other part, wherever I can go, I can avoid them, is that nowhere dense. So this is somewhere not dense is the negation of the property of everywhere dense. After all, it's raining everywhere. What is the negation? Somewhere it's not raining, that's all. It is not everywhere it is not raining. Okay, that's, should be very careful, that's a very strong negation actually. So now the third one is that. The third one, the S3, is nowhere dense. Whatever portion you take, you can always find a sub portion which avoids integers. Right? So here S3 is nowhere dense. That is, whatever interval, open interval, a minus epsilon, a plus epsilon, we take in R, we can find an open subinterval such that it has no points of. How do I find that? Take an interval. There may be some integer points. I don't know whether they are integer points or not. Suppose this is the portion I took. This is a and this is a minus epsilon, this is a plus epsilon. If this fellow has no integers, I have already avoided the set here. If this fellow has integers, then it may have one or two. If he has one fellow, avoid that portion and take the remaining part. Still I have avoided it. If there are two integers, take the portion between them, you have avoided it. Therefore, wherever you go, you can avoid them. Okay? So that is what is meant by nowhere dense set. Wherever you go, you can always find a subinterval that is free from this set here. So there is everywhere dense, somewhere dense and somewhere not dense, and nowhere dense. Now this definition has nothing to do with the real line or the interval. This is simply the role of the open ball that is played. So the general definition is now, in a metric space, omega t, a subset S is called a nowhere dense set if for every that ball has, the open ball, B epsilon x has an open sub ball B epsilon 1 x1, some other center which is contained in B epsilon x, such that it is free from points of. So you go to any place, reach any center and any radius, then there is a point inside that, such that if you draw a sufficiently small enough radius of epsilon 1 around it, no S points. There will be no S points.
We also say that for every x, there exists some epsilon ball around it, which does not contain point from that.
Even is a sub ball. It need not have the same center. Okay? It could have a different.
The center belongs to it.
Yes, there is a subtlety there. There could be some other center. I can't say that with the same center there will be a sub ball avoiding that point. Okay? So I have to say that there is some sub ball which is avoiding. For example, here we look at a finite set. What can you say about a finite set? It will be nowhere dense. You can avoid one, take a ball. If it is another point, draw a smaller radius, and finally you will avoid all the points. The finite set is nowhere dense. We already know a countably infinite set which is nowhere dense, namely the integers. So we could have very big sets. Now what this says is, there is this, we must be very careful when we use the word negligible. See, the word negligible is extremely dangerous stuff. For example, 0.1 millimeter may be negligible for someone, depending on what technology you are in. But for some other fellow, very sophisticated technology, 1 millimeter is too huge a loss to be negligible. So you must be sure about what context you are in. So this notion of very small set is in what context? From the set theoretic point of view, we treat countably infinite sets as small sets. That is the maximum infinity we allow. I mean, the smallest infinity we allow. So we think of that, okay, that I can handle. From the set theoretic point of view, it is a small set. From a measure theoretic point of view, it's a small set. Later we'll see the measure of a countable set is 0. I mean, at least Lebesgue measure. From topological point of view, it's a small set. It is nowhere dense. It's very sparsely distributed. Okay, basically you can avoid them. They're irrelevant. I can always avoid them, sort of thing.
Q turned out to be dense.
Huh? But Q turned out to be countably infinite, but also dense. So therefore, countably infinity may be small from the sense of cardinality, but it is not possible to relegate it to smallness from a topological sense. The rational numbers are countably infinite, but they are very important set, they are dense. They cannot be relegated to a smallness in that sense. So smallness has to be very carefully worded. Countably infinite set is small from the set theoretic point of view, but not necessarily small from a topological point. Of course, from a Lebesgue measure theoretic point of view, it is small. Okay, still the Lebesgue measure is 0. So there are lots of things that you should keep in mind. Are you doing algebra? Are you doing set theory? Are you doing topology? Or if you are doing all of them, you better be careful, very, very careful when you use the word small, big, negligible, etc., etc. Okay. So at any rate, we know we can have countably infinite sets which are nowhere dense. There are countably infinite sets which are nowhere dense. So, can an uncountably infinite set be nowhere dense? That looks very unreasonable. It's so huge. And unfortunately, there can be. There can be uncountably infinite nowhere dense sets also. Now write in the bracket Cantor's at least N is a countably infinite dense. The interesting thing is set theoretically huge fellows can be topologically small fellows. So this is something which you should keep in mind. Okay. Now, the rational numbers, we found they are not nowhere dense. In fact, they are everywhere dense. However, they are made up of nowhere dense set, singletons. A countable number of nowhere dense sets put together gave me the rational numbers. So at the lowest end are these nowhere dense sets, and then I try to build up, starting from a nowhere dense set, what are the things I can build. So suppose I have two nowhere dense sets. So suppose A and B, A1 and A2 are nowhere dense sets. Then I can look at their union. What I generally put together, I allow in all these operations is finite and up to countably infinite. So I like to have a countably number of, so suppose An is a countably infinite collection of nowhere dense sets. I will write NW. Now suppose I have a collection of nowhere dense sets. Then the rationals tell us it is not necessary that their union be nowhere. So it is not necessary. See, it is not necessary that union n is nowhere. For example, Q is equal to the union of all the singleton QIs. Each one of them is a nowhere dense set, but however, the union is not nowhere dense. So in other words, what we say is, by putting together nowhere dense, you may get a different type of set. It is not nowhere dense, but it's the atoms that go into building it are nowhere dense. So in other words, use certain types of fellows, build something new. Use only nowhere dense type fellows, but you have built something new which is different from nowhere dense. Now, if I can, the question was whether I could put together nowhere dense set and get everything. Well, I at least got rationals. I can get rationals. So I will call a set to be a set is contained in omega d is said to be of first category if it is a countable union of nowhere dense sets. Like the rationals. Therefore, for example, Q is of first category. Okay? Now, of course, the terminology that I have used, first category, already suggests that there is going to be at least one second category, if not more. Okay. So, what is again the building process? Can you start with certain types of fellows, and you do in topological thing you are only allowed set theoretic operation. The simplest set theoretic operation is putting them together, the union. If I start unioning the simple fellows, what do I get? You start getting new things. So give them name. The moment you find a new thing, give them a name. And that name is first category. First I don't give a name. I found that there are others who cannot be achieved this way. The question was, is there any subset of the real line which cannot be built up like this? Or is every subset of first category? The question is, can every subset of R be built like this? Question is every subset of, first I will stick to R of first category. That is, if S belongs to R imply S is equal to union Sj, j equal to 1 to infinity, Sj nowhere dense. Can every S be written as the union of nowhere dense sets? Countable union of nowhere dense. Now, before I answer this question, I want to look at two remarks. One, I said forget about it. I got first singletons, they were nowhere dense sets. I put them together, I get a set of first category. Now I start putting together first category sets, what do I get? So I got new, like in the institute we had to go on doing it. 70 years back we had red oxide floors. Then suddenly we decided to do some research and found that this thing can be made into mosaic. We removed all that and put mosaic. We got newer things. Now we have vitrified and all kinds of tiles. We go on changing them and get more and more flooring done. See, most of the time, and somebody will come up with vastu and then we'll start breaking and put another new thing, build another new thing. So from the old ones we start building new ones. The moment you get new one, from that you build a newer one. So I got first category sets. If I put together first category sets, what will I get? If I put together two first category sets, what do I get? The first fellow is the union of nowhere dense set. The second fellow is the union of nowhere dense set. But this is a countable union, this is countable union. If I put together, I still get a countable union. So still I get only first category. If I put three first category, nothing. If I put countable number of first category sets, nothing. So the first category doesn't generate, your research is over there. Okay, thesis should end. You must, or one chapter is over. Okay. So the union, I'll just write this, of a countable number of first category sets is of first category. That we see. Now, we saw that the rational numbers are of first category. And suppose the irrational numbers are also of first category. Suppose, we don't know. Suppose the irrational numbers are also of first category. Then their union must be first category, but that's all of real numbers. So the entire real numbers will become first category. And therefore, many things will follow. Okay. So if we don't know this, if the set I of irrational numbers is also of first category, then Q union I, which is equal to R, will also be of first category. Now at this stage, Baire, there is a very famous mathematician, analyst, Baire, by name Baire, B-A-I-R-E, he was very fond of this sort of constructions. Start for something, put countable number of them and see what happens new. You start something old, through that I do natural processes, what do I get new? We had lots of Baire class of functions, Baire class of sets, Baire categories of sets and so on and so forth. And Baire showed this cannot happen. The real numbers cannot be of first category. In general, no complete metric space can be of first category. So that's a famous, that is called Baire's category theorem. No complete metric space can be of first category. So anything that is not of first category is called second category. Okay. That is a complete metric space is of second category. That's a very that was a theorem which this theorem plays a very fantastic central role in many important theorems in analysis, and functional analysis also analysis for me. So it plays a very central role in some of the major central theorems in analysis. So it's a very important theorem. I remember about 30 years back, maybe even more, sometime around 1973, we had a binational conference, Indo-US, Joint National Science Foundation Conference in mathematics. At that time, the NSF asked that a small workshop be organized for gifted students in mathematics, both at the undergraduate as well as the postgraduate level. And I was one of the persons who was asked to organize this postgraduate MSc student. The topic we chose was Baire Category theorem and its applications. It was just all those interesting results that come in analysis starting from Baire Category. And we couldn't cover everything. Because first part of the course we had to develop all these things and come up to what Baire Category theorem is and give a lot of metric spaces, examples and so on and so forth. Then come to this various. But you could, what I would say, there are so many theorems that fall out of Baire Category theorem. Okay, now, if this theorem, because of Baire Category theorem, R cannot be of first category because R is a complete metric space. If it cannot be of first category, therefore I cannot be of first category. Therefore I has to be of second category. The irrationals are of second category and the rationals are of first category. Because if the irrationals became second category, first category, then the reals will become first category, which will contradict Baire's theorem, and therefore the irrationals form a set of second category. So there is a certain amount of interpretation of how small or how big these sets are. And in a sense you treat first category also as, well, they may be dense sets, but they are somewhat sparse, in a meager or sparse, or all kinds of adjectivized words are used. But nothing, you may start splitting that word into pieces. No, it doesn't fit, rational numbers doesn't fit the exact literal meaning of this word and so on and so forth. Then there will be a problem. See, sometimes English words you must take it on face value and leave it at that. I just, before coming to the class, I was reading, who gave me that book? Yes, the random books inside. There was one small joke that was put there. That is, this is a standard joke which everybody knows. One fellow tells a humorologist, I heard this very famous joke. The physicist was telling his friend that this world will come to an end in 15 billion years or something like that. And then the fellow was playing poker next to him, so he said, "What did you say?" He said 15 billion. Thank God, I thought it was 15 million, he said. So there is something like, it is irrelevant for that poker player who is 15 million or 15 billion, he is going to die anyway before that time. But then the humorologist did not laugh. He was just sitting there for 10 minutes, and then after 10 minutes he started laughing loudly. Then this guy asked him, "Why did it take so much time? Did you not understand that joke?" He said, "No. Before I understood, decided, I have to make sure that it satisfies all the definitions of a joke, humor." So he is Kant's definition and somebody else's definition, and verified that all the, therefore this is a joke, now I laugh. Okay? If you end up like that, life is miserable for you. Okay, so therefore we are very short of words. So the word meager is meager to explain everything that we mean. So therefore, the sets of first category topologically must be thought is somewhat of weak, very weak. Okay, they may be dense, but at the same time they are made up of very small, insignificant fellows. We can build them up from insignificant fellows, but it doesn't mean they are insignificant. That's also a moral. Lots of insignificant fellows put together doesn't mean they are insignificant. A lot of these nowhere themselves put together become highly significant. Okay. Now, I want to give one simple situation of this Baire category theorem. Before that, a normal definition of nowhere dense set that is given is the following, which looks very non-motivating, but we can show that these two definitions are equivalent. Okay, so therefore we will state that as a proposition. Before I state that proposition, let us look at a nowhere dense. First, what is the motivating factor of that proposition? Suppose you have a nowhere dense set. Suppose S is a nowhere dense set. Okay. Now, Suppose x belongs to S. Take any point that is in X and then draw any sphere about it. What can you say about it? Now, because it is nowhere dense, there will be a small patch inside this. This is free from S elements. What can you conclude?
Can have no limit points.
Yes?
No limit points.
No. Okay. Even simple. Right. Forget about limit point and all. Just looking at the picture, a very simple conclusion straight away. I want to come to limit points also. But it's a simple conclusion.
Economic connection.
I have not introduced the notion of connect. Very simple thing.
The patch itself is dense. Patch itself, whatever.
See,
it's
there is
known
no
for.
trick in this question. So, all may be right. But I want a very simple observation. Whatever ball you draw about X, it cannot be completely in S. Whatever ball you draw about that point X, whatever radius, epsilon, that entire ball cannot be fully in S. What does that mean? It cannot be an interior point of S. What is meant by an interior point? The whole neighborhood must belong to that. Now whatever neighborhood I take, there is a small patch which is free from it. Therefore, X cannot be an interior point. So what it says is, X cannot be an interior point of S. So this implies every open ball about X has set elements from S prime, which implies X cannot be an interior. So the interior is empty. No point of S can be an interior point of S. So S, the interior, is empty. No point of S can be an interior point. So therefore, the interior is empty. Now if you carefully look at the limit point thing that he raised, you could go one step further and show this. A set S is nowhere dense if and only if not only the interior of S but the interior of S closure is empty. So along with S you take the limit points of S also and take the bigger set and still look at the interior point. No point can be an interior. That's a simple proposition. Actually this will be what most people give us the definition of nowhere dense set, but that doesn't motivate me what is happening. Nowhere dense means I go somewhere, I will avoid it. Wherever you go, I can avoid it. That's a natural way of looking at it. So therefore, I always prefer the other definition, and this comes out as an equivalent format of nowhere definition, nowhere dense sets. Okay. So therefore, I am going to look at Baire's theorem in a different language. Baire's theorem can be looked at as follows. Here, Baire's theorem can be looked at as follows. Suppose omega is a complete metric space. S1, S2, etc. are closed sets in omega, and omega equal to the union of Sj. What can we say? What does the Baire's theorem say now? Baire's theorem says that no complete metric space can be the union of nowhere dense sets. Well, therefore, since it is the union, if every one of them becomes nowhere dense set, it will violate Baire theorem. So at least one of them is not nowhere dense. It doesn't mean everywhere dense. Okay, you should be very careful. So at least one of the Sj, say S capital J, is not nowhere dense. Now what is meant by nowhere dense? The interior of the closure is empty. Now I will use that. Nowhere dense means interior of the closure is empty. Not nowhere dense means the interior of the closure is not empty. That is Sj what is the closure? Itself, because they are all closed sets. So the interior of the Sj is not empty. Interior of J is not empty. So you can interpret Baire's theorem in this way. There are various ways of writing Baire's theorem. The Baire theorem says, if by chance you have expressed a complete metric space as the union of some closed sets, then one of them must have an interior. One of them must have a ball inside it completely. An interior point, therefore the entire ball must be inside. So one of these sets must contain an open ball. Okay, that's what is the other way of looking at Baire's theorem. It is in this form, it will be repeatedly used. It is this form of looking at the Baire's theorem that it will be repeatedly used. So the next 10 or 15 minutes, I will just give you one, I don't know, I will try to reduce the example to the minimal level. Now that I have only 15 minutes, the minimal level is the complex thing. But well, let me start with a very simple example. I mean, how we use it to get some very fancy results. Now suppose, you all are familiar with complex variables, simple things and analytic functions. You are familiar. Of course you are familiar. That is the final proof. Of course you are familiar. You know what is meant by an analytic function. Well, even if you don't know, you know what is meant by differentiable function. The derivative exists, then it's called differentiable. So I am looking at where the derivative exists at every point in the complex plane. They are called entire functions. A function which possesses a derivative at all points in the complex plane. Okay. So let me look at entire functions in C. What are they? They are functions from C to C such that f prime z exists for every z in C. Any example? Constant. The derivative exists at every point, fz is equal to 4. Fz is equal to z. The derivative exists at every point, it's 1. Fz is equal to z square. The derivative exists at all points. Fz is equal to z cube. Derivative exists at all points. In general, fz is equal to z to the power of n, where n is a non-negative integer. The derivative exists at all points. If two functions have derivatives, their sum has derivative, difference has derivative, constant multiple has derivative. So if I put together all these z to the power of n's, what do I get? A polynomial. So polynomials are the simplest starting points of entire functions. So example, do you know any polynomial z is an entire function? Any other entire function you know? Exponential z, e to the z, sin z, cos z, all are entire functions, not tan z. Tan z is not an entire function. Well, our concentration is going to be with polynomials today, okay, for this example. Now, a typical property of the polynomials is, if we take a polynomial, say of degree 10, okay, what happens to the first derivative? Ninth degree, at most 9th degree. It could be 8th degree also. Okay? It could be, well, it depends on, okay. Let's say it's 8th degree. If you already have 9th degree, 9. Next derivative, 8. Next derivative, 7. Next derivative. So if you differentiate sufficient number of times, what will happen? It will be 0. Okay? So, if Pz is a property of a polynomial, if f of z is a polynomial, then there exists a non-negative integer k such that the kth derivative is equal to 0 for right?
So this differentiation is like
These
between
are-
R2 to R2.
Yeah, this is a complex differentiation. Fz plus h minus fz by h, where h is a complex increment. Of course, if you want to talk about differentiation from R2 to R2, if you look at the differentiability criterion carefully, both are same. Okay? What is differentiability of function of two variables? Then both will be the same. Let's think of it simplest ways. Look at it as a complex function of a complex variable. They have the standard differentiation equation. Okay. But the Cauchy-Riemann equations is essentially the condition of the fact that the map f R2 to R2 is a differentiable map. Okay, these are the. Let's not get into that. You have a normal idea of a differentiation. So what is meant by the derivative of fz? You look at a complex, give complex increments and look at fz, look at differentiation. This limit exists whatever way h approaches 0, as long as mod h tends to 0. In complex plane, there are various ways we can approach to a 0. Okay. All the directions, all the curves, everything must be the same. Right. Okay. So let's do. So now, if I know, when I say what is meant by a property, I am not going to add, it's a characterizing property of a polynomial. What do I mean by that? If I know it's a polynomial, I know this happens. And if this happens, it must be a polynomial. If the function is such that there is a particular order derivative which vanishes at all points, then that has to be a polynomial. That is a very important result it has to be proved. It's non-trivial. Okay, so at least 2 lines one has to write to get it proved. But intuitively we all know we can go on integrating back. Suppose f10 is 0, f9 must be constant, f8 must be cz plus d, f7 must be cz squared by 2 plus dz plus e. So like that you will pick up all the derivatives. So intuitively we see that if this happens, then it must be a polynomial. So a characterizing property of the polynomial is the fact that there is one order such that that order derivative is 0 at all points, and conversely, if a particular order derivative vanishes at all points, that function must be a polynomial. This is true even in real numbers. If I had functions on 0, 1 to r in the interval, if it's a polynomial function, then certain order derivative will be 0 at all the points x. Conversely, if fx is a nice continuous function which has all the derivatives up to order 10 and the 10th derivative vanishes at all the points, then the function must be a polynomial. Up to this, it is irrelevant whether they are working in the complex situation or the real situation. The same ideas will go through. Now, I ask the question. I wanted to prove that something is a polynomial. I wanted to check whether something is a polynomial. Now if you wanted to check whether it's a polynomial, one way is to check whether there is some order derivative which vanishes at all points. But when I try to do it, there are certain difficulties that I have. So what I am able to do is, I am able to do 10th derivative vanishes here, 21st derivative vanishes here, 56th derivative vanishes there, 87th derivative vanishes here. So the order I get depends on the point at which I am looking at. So suppose for every z in C, there exists a non-negative integer kz depending on z, such that the kz derivative at z is 0. You see now, formerly we had the same order derivative vanished at all the points. Now at different points, different order derivative vanish. But I know definitely that at each point, at least one order derivative vanishes. At this point it may be 10th order, at point may be 24th order, another point it may be millionth order derivative. But the fact is, at each point there is at least one order derivative vanish. Can I conclude it's a polynomial?
Take the maximum of
Yeah.
maximum of order.
The maximum could be infinity. See, at one point it may be 1, the next point it may be 2, next point it may be 3, next point it may be 4, and it may be blowing up. So the order may be infinity, then you are in trouble. The maximum could be infinity. Okay? So that's what the problem. When you are taking maximum over infinite number of fellows, be careful. So can we conclude Fz is a polynomial? Interestingly, yes. And that's Baire Category. There's Baire Category theorem comes. So I'll try to indicate the proof in five minutes. And I'll show why I chose complex and not real, because complex at one stage the whole thing collapses and you have the answer. But in the real you have to work much more from that stage to get to the final answer. Okay, so first of all, I'm going to let the answer is yes. Even if you are able to show that at each point some order derivative vanishes, eventually you will be able to get hold of one order which derivative vanishes at all the points. That's best. That's a remarkable theorem of characterization of polynomials. And okay, let's see. Suppose I define the set as Sn to be all the points that belong into C, such that the nth order derivative vanishes. So in other words, what I do is I go and collect all those points at which the function is 0. I call it S0. I go and look at all those points where the first derivative is 0. I call it S1. I collect all those points where the second derivative vanishes and I call it S2. So Sn is the set of all those points where the nth derivative vanishes. Now is Sn closed? Why? If you take a sequence Zk in Sn, Fn Zk will be 0, but Fn will be a continuous function. Because I have to take that it's an entire function. Okay, where is that? All the time, F is entire, and therefore the zeros of a continuous function form a closed set. Okay, that's a very simple thing. The roots of a continuous function will always form a closed set, and these are the roots of the nth derivative function, which is a continuous function. Okay, roots of a continuous function, therefore closed. And we will see this property in more detail when we discuss continuous functions. Okay.
And every point is.
So Sn is a closed set, and the union of the Sn is C, because every point will belong to one of the Sns, because some derivative will have to vanish, but particularly Z will belong to Skz, isn't it? Because the kz derivative vanishes at Z, So it will belong to Sk itself. So all the points will belong to one or the other. So C is the union, but C is complete. What does that say? Therefore, there exists an Sn such that what? The interior of Sn is not empty. What does that mean? There is a point such that there is a whole disk around it which is in Sn. So that means there is a disk, there is a point U and the radius epsilon. This is contained in Sn where U belongs to Sn. For some U belonging to Sn, epsilon greater than 0. Because U is an interior point. It must have a whole disk about the open the balls in the plane are the disks. So what it says therefore is all these points are in Sn. That means f and z is 0 at all z in Sn. That says it is a polynomial in the disk. But if it's an entire function coincides with the polynomial in a disk, it has to be a polynomial. That's the beauty of the complex function theory. Okay, so this says fz equal to a polynomial inside Sn. But not inside Sn.
It's not Sn.
Not inside Sn. Inside that ball. What is that ball? For all that in P epsilon inside P epsilon. So here is one entire function, here is another entire function, the polynomial. If two entire functions coincide in a disk, they have to coincide everywhere. So this is the power of, if this is a theorem in complex, if two entire functions agree on a disk, in a disk, they agree everywhere. This is the power of the complex analytic functions. And therefore, fz must be equal to the polynomial everywhere, the same polynomial. Okay. So that's a characterization of complex polynomial functions. Even if you are able to show that at each point some derivative vanishes, that's enough. You don't have to waste your time trying to find the same derivative vanishes at all those points and so on and so forth. Essentially, it's enough if we show that somehow a derivative vanishes there. That's enough for me to conclude it's a polynomial. Now, if we do in real line, what will happen? I will start with this. I will not call entire functions. I will call C infinity functions. So I will have 0, 1, say suppose I have 0, 1 to R, C infinity functions. Then I will say it's a polynomial. Any polynomial in X is a C infinity function. And if I have a polynomial, some derivative will vanish at all points. Conversely, if the same derivative vanishes at all the points, it must be a polynomial. Question: if for every x in that interval, a non-negative integer kx such that this happens, will it be still a polynomial? Go through this. Construct Sn. Now what will be Sn? It will be x contained in the interval 0, 1, so that the nth derivative vanishes that. You get this. 0, 1 will be equal to this. 0, 1 is a complete metric space. So you will come to this, and therefore you will get some, instead of a ball, I will get an interval, in it is a polynomial. So I will say f is equal to polynomial here. But this is only a part of 0. From here, to show that it is polynomial everywhere else is a hard work in real analysis. But in complex analysis, that one theorem, that if two analytic functions match in a small patch, they'll match everywhere, forces it to be a problem. So complex function theory is much easier than the real function theory. So complex is a wrong word for that. It is simple. Complex function theory is more simple than simplex function theory.
Such functions are restriction of complex functions, right? In a
Which one?
sense.
No. Every C infinity function on the real line does not have an analytic continuation into a complex analytic function. That's the problem. Okay. So, there is a lot of difference between a real C infinity function and a real analytic function. Okay, now that Baire is over. Okay, now it's only answer. So the Baire's, I will come back to your question. Now that you raised that question, Baire's category theorem will give you such very surprising results. Many times you will pull out this Baire's category theorem from nowhere to get some very interesting results in analysis. Okay. There is similar characterization of the opposite of differentiation is integration. So what we are saying is you differentiate k number of times, that becomes 0. Suppose I integrate indefinite integral k times k times k, go on integrating backwards. Okay, and something happens for a particular k. For the same fixed k, something happens. Like the kth derivative vanished, the kth integral vanished. What can you conclude? Suppose integral ft dt is equal to 0. K times 0 to t, 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 0 to t f dt, f ds is 0. What can you say about that function? First of all, suppose 0 to t fs ds is equal to 0. What can you say? If 0 to t fs ds is equal to 0 for all t, 0 1 syllable. What can you say about that function? Very interesting. Okay. Okay. Suppose I have 0 to t. Let me write that. For all t it's 0 1. I have a nice function. Let's forget about the conditions. You think about it, then we'll see what our conditions require. Suppose I have a function 0 to t. F is defined in 0 1. Fs ds is equal to 0. What can you say about this function? It must be 0. It must be 0 everywhere.
No, that's what it
Is that true?
right?
That is one of the solutions. Huh?
From
What can you say about this function?
After for x greater than 0, it is 0.
Hmm?
Negative ತಗೊಳಕ್ಕಾಗಲ್ಲ. The same sign but it's 0.
Okay. It's indefinite integral for all t.
For all t.
It has to be? It has to be?
0 after 0.
Okay. So I'm going to give you a question mark here. Next, what happens to this? Let's say you do double. Suppose this is equal to 0 for all t. Okay. Now this is exactly the reverse of that process. There we are differentiating or doing integrating. Integration is the opposite direction. Opposite direction, more and more smoothness keeps coming. Now suppose like this, you go on doing k indefinite integrals and that is equal to 0 for all t. 0 to t, u, v, w, etc. And then final integral is ds. Okay, whatever that is. You do so that is equal to 0 for all t. Then, what can you say about that? There is a certain conclusion I am going to make. I am not going to tell you. I want you to think about it in the weekend. then the same question arises. Instead of all being 0 for all t for the same k, for each t there is a particular level backwards integration you do which will give 0. Can we make the same conclusion? And the answer is again yes. Okay. So that's the sort of results that you get. But these are two strange results which strangely are not many times mentioned in many textbooks. Okay. This characterization of polynomials, etc. But coming back to the question that you raised, there is, if we have, let's take complex, the whole plane itself, let's not even look. Okay, take a domain in the complex plane, some portion of the complex, like the disk, unit disk. Suppose you have a function which is differentiable at every point in that domain. That is an analytic function in the domain disk, unit disk. Then it is forced to have all derivatives. That's a very fundamental property of analytic functions. If it has one derivative, it must have all derivatives. So it's forced to be C infinity function. And every analytic function has a power series. The Taylor series expansion in the neighborhood of a point of analyticity. So in particular with the center you can write a power series or a Maclaurin series. But if you come down to the real line, instead of the disk I have the open interval, say -1 to 1. And I have a function which is differentiable there. I can say nothing about the second derivative. It may be differentiable once, but the second derivative may not exist at all. So there is no way to go from first derivative to second derivative in the real analysis case, where it is guaranteed when you are dealing with analytic functions. And suppose I give you that also, okay, all derivatives are there. I have a function which is infinitely differentiable. Then is it possible to expand in Taylor series? That I still cannot say. There are functions which are infinitely differentiable, but which cannot be expanded in a Taylor series about a point. So therefore, this whole idea of analyticity is different from C infinity when you are in the real line. In the real line, analyticity is different from C infinity. What is analyticity in the real line? If it is not only C infinity, but it can also be expanded in a Taylor series, that has to be added. Whereas in the analytic function theory, that addition was not needed, it was all guaranteed by the properties of analytic function. So the analytic function theory is a much more powerful theory. And therefore, that one theorem of Cauchy takes care of several things in the real life, which we struggle. Real analysis, therefore, is a little more involved than complex analysis. Whereas in complex analysis, if you have a function differentiable in a domain, all derivatives are guaranteed in that domain, which is not so in the real. It has its pluses, it has its minuses. And you have to do, the moment there are pluses and minuses, you have work to do which is plus and which is minus. When it is minus, what are the extra things that you have to do, and things like that. Like here, the extra thing will be phenomenal. Just from one disk we pushed it off the whole place, but it is not so in the real life. You have to do much harder work to eventually conclude that it is a polynomial. But the result is true. Result is true. Up to that is Baire's theorem. Then is repeated application of Baire's theorem and then some manipulations to get to the final step. Whereas in the analytic case, it is automatic. So this idea of nowhere dense is a very important notion, which leads to the notion of first category and the important theorem of Baire. Baire's theorem is a very central theorem in analysis. It gives very important theorems like open mapping theorem, uniform boundedness principle, all kinds of things. The first step, major step, is to set up a complete metric space that the union of closed sets, conclude that there is a ball, the rest of it follows. Okay. The rest of it is only technical detail. This will be the first major step in all these fields. Okay. So all of you send me a blank mail, or whoever is willing to continue in the August term, send me a blank mail again. So I will create a new list. Maybe in the end of the first week of August.